Good morning, everybody, and welcome to this week's installment of training with DeZURIK. So in this session, we'll define what we mean by hydro, describe where Hilton valves may be found in a hydro system, talk a little bit about how head is used in the industry. It's a little different than maybe other industries. Then review some types of dams, their common features, and importantly, what is currently driving the hydro valve market. Then I'll describe a typical case study where a Hilton valve has been installed at a dam, and then finally wrap up with reviewing the three types of hydro valves that Hilton fabricates. So hydro in the Hilton world is anything associated with dams and the passage of raw water through or over them, and that includes the transmission or conveyance systems between them. You notice here on this graphic, there's two types of dams. There's powered dams and non-powered dams. It's interesting to note that there's about 80,000 dams in the US, only about 2,400 have powerhouses on them. So the vast majority would fall into what we consider the municipal market, and lesser in the industrial side. So where are valves located in a typical hydro system? Well, you'll see them in larger powerhouses. You might see them as in ancillary systems such as drainage or cooling water systems. You'll see them in the conveyance, along the conveyance system, in valve stations or along the pipelines. You'll see them in the outlet works, and that's the system, that's the facilities that let water out of a dam. And occasionally you'll see them associated with a fish passage system to get fish up and downstream around the dam. So let's start out first by talking a little bit about head and how it's used in the hydro industry. So dams are designed by civil engineers, geotechnical engineers, so they're used to thinking of things in terms of head versus PSI. So they consider a low head dam anything 35 feet in height or under, medium head dam between 35 and 350, and a high head dam over 350. You note down here below conversion between PSI and feet. And the vast majority of dams in the US are really low head or low medium head dams. The higher head dams are the more visible and get the most press, but they're really in the minority. So a few head terms that we need to establish. The gross head is what we would call static head. It's basically the difference in elevation between the reservoir, top of the reservoir, and the center line of the pipe that our valves installed in. Net head is dynamic head. Once the water is flowing through our valves, then it's the pressure that you would measure either in front of the guard valve or the outlet valve. That's important to note because if you ask us to size a valve, we size valves based on the net head. So the pressure right at the valve is what we size the valve on. If they only give us the gross head, then we have to ask them, okay, what are the losses between the reservoir and the valve? Because that can reduce the head. Unbalanced head is when you have one side of the valve is completely sees full reservoir head, and the other side is atmospheric or something less. So that's important to note because unbalanced head is it makes us choose a different size or resistance pressure rating valve than we would if it was a balanced head. So balanced head is when you have the same pressure on both sides of the valve, and the valve is operated with pressure on the same on both sides. So let's talk a little bit about dams, the types of dams. There's more than the types I'm showing here, but there's I'm touching on like the four most common types. So typical dam features. You've got your reservoir, the dam, and the tail race are the three major civil engineering elements. Then you've got the inlet works to let water into whatever conveyance is passing water through the dam. Then you've got outlet works for letting the water out. The reason dam designers like to use inlet works is because they don't want to have this pipe, say, between the reservoir and the outlet works fail and compromise the dam. So they want to be able to shut the water off in the reservoir or on the upstream face of the dam. Some of the other features are spillways, and then roller gates and radial gates. That's two things to note. Sometimes you'll hear the word gates. You want to make sure that you understand what those gates are. They're not, in the hydro world, gates are not valves. So a roller gate is a large bulkhead basically with wheels on it. And a radial gate is also known as a Tainer gate, are large gates that are installed at the crest of the dam for passing flow over the dam. So a few types of dams here. Storage dam, these are the ones that most people think of because they're large and visible. So Grand Coulee is an example of a storage dam. They're large storage volumes. Often, as in the case of Coulee, they're located on the upper end of a river system. So the Columbia River, this is sort of like the control that controls water downstream to the other dams. Although this one is concrete, today dams are made really with roller compacted concrete or some kind of earth construction because it's just cheaper to do. Concrete dams are really expensive. A little bit about the owner. So the Bureau of Reclamation is the owner-operator of Grand Coulee. Most dams in the U.S. are either owned by and operated by federal agencies such as the Bureau or the Corps of Engineers or TVA. Then you'll have your investor-owned utilities such as PG&E or Florida Power and Light, Con Ed, Duke. Public utility districts. So up here we have Grant County PUD or Chelan County PUD. And finally, you'll see state and local agencies such as in California, the Department of Water Resources, or in New York DEP own and operate dams. So run-of-river dam, these are installed on most of the large rivers in the U.S. So the Missouris, the Columbias, Mississippis, and they're predominantly Corps of Engineer facilities because the Corps' mission is to control flooding and to facilitate boat travel. So there'll always be a lock associated with a run-of-river dam. They're not really high head. The Dallas Dam here I'm showing on the Columbia is only about 80 feet ahead, but it's a huge flow, so it still produces a lot of power, like 1,600 megawatts. And these days almost every run-of-river dam has some kind of fish passage, fish ladders to get fish upstream around the dam. Diversion dams are smaller dams, usually low head, minimal storage, and they're used to aggregate flow from usually streams and creeks higher up in a mountain into a tunnel or something to get the water aggregated and into a powerhouse or something downstream to make power. Finally, afterbay dam. Since a power dam, designers of turbines like to have the turbine see a constant head. It's common for them to install a afterbay dam downstream of the power dam, and that creates a constant head that the turbine can then just operate and see the same head and not have to worry about adjusting the flow through the turbine. This is the Tiger Creek afterbay dam in California on the Columbia River. Why is water being released from dams more? You'll probably get requests, from customers saying, "Hey, I need to replace a valve or enlarge a valve on my outlet." Why is that happening? Well, there's three main reasons. One is that lawsuits have basically said, "Hey, you need to restore the river downstream of your dam. It's been there for years, and you're just not letting enough water downstream. We want to restore the downstream conditions." Another one, important one, especially up here in the Northwest, is to improve fish habitat, fish passage. So fish, if the water's warm, for instance, a salmon won't migrate upstream because they're looking for cold water coming off snowmelt. So regulators up here are telling dam owners, okay, you've got to release more water, cooler water, and then during the seasons that fish are migrating, you can't just do it when you want to. You've got to do it on a schedule. And finally, there's a small, stakeholder group that says, "Hey, we'd like to do whitewater rafting or kayaking or inner tubing," and you're drying up the river. So all three of those reasons are why dam owners are being asked to release more flow, which in many cases means open a valve that they haven't opened in a long time or increase the size of that valve. So just to recap, where is water released from dams? There's spillway, which is spilling over the top of the dam. There's the turbine discharge if it's a powered dam. There's a turbine bypass valve. So that's basically if the turbine trips, it opens to make sure that the river downstream doesn't dry up. And then finally, the outlet works. And again, that's the most common place that Hilton valves are installed. It's either I show internally or externally outlet works. So let's talk about internal outlet works. It's common to see valves installed in the middle of a dam, some kind of a gallery or chamber in the middle of the dam, with inlet works letting water through those outlet works. Notice I've got air coming into the valve chamber. That's important for any kind of valve releasing flow because you need to aspirate the valve and make sure it can pass water if you don't have vibration and pulsation. And then external outlet works is just moving the valves to the downstream side of the dam. So there's a lot of older dams, built in 20s and 30s that this is their typical construction. The designers or the builders put an inlet, uncontrolled inlet on it called a grizzly, just a bar rack basically, and then just a gate valve on the discharge. And these were also called sluice outlets because they basically were installed so that if the reservoir silted up, they could occasionally open them and just sluice the sediment downstream. So this is an example of an older dam inlet and outlet works project. This is a project that that Hilton Valve provided some valves on. It's Meadow Lake Dam. It's high in the Sierras, Northern California. It was built by PG&E basically to just store water that they could make power with when they needed it. And in the summertime, when everything was drying up, they could just release water from this dam. It was also used for recreation. And in 2004, they were told, hey, you need to release water downstream more than you're doing. So the project was to improve the outlet works. So as an engineer with DTA, I was fortunate to be able to go up to these sites, which are just beautiful. This is just north of Yosemite. This is a helicopter shot going into the project. And you can see that when this snow melts, it probably comes down pretty fast because that's solid granite. So at Meadow Lake, this was the reservoir dewatered. This is the grizzly I was talking about, just a simple bar screen. And this is what it looked like on the downstream face of the dam. Just a couple of pipes, probably 24, 30-inch pipes with a couple of old AWA non-rising stem, looks like gate valves. So this was how Hilton Valve provided a valve. So those same two pipes, they chose one to be the controllable line and the other just to be a backup line. So we installed our Hilton 360 throttling knife gate on the control side. And then they elected to use just another non-rising stem AWA valve for the guard valve upstream of it. Interesting on this project that because these are so remote, there's no power up there. So they tap the line here on the right side, the small 8-inch valve that runs a turbine generator that generates power to charge batteries that then ran these 24-volt actuators on the valves. And this is the type of valve house that PG&E built back in the day. This is redwood, just beautiful, sheathed over a CMU building. So it could be that the regulatory agency said you needed to make this look like a cabin or something, but it's a beautiful building. And then also note the face of the dam there is granite slabs. So the story there I was told by PG&E is that the Italian stonemasons that built Washington, D.C., many of the buildings in D.C., wanted to stay in the States, so they migrated west and then found, hey, they're building dams and they need some facing put on them. So these dams were faced by the same masons that built Washington, D.C. And then finally, this is how, because they are so remote, this is how our valves made the last leg into the project. So a truck would go as far as it could, and then PG&E would have I think they used one of their own helicopters to bring the valves in. So what type of valves do we supply to the hydro industry? There's three basic types. The throttling knife gate, our series 300, 360B throttling knife gate are good for using on outlet valves and guard valves on low to medium low head dams. So this photo here is the Pitt River in Northern California near Lake Shasta. This is I think it's a 90-inch throttling knife gate. Low head, maybe 25 psi. So it's the throttling knife gate valve is basically our bread and butter 200B knife gate valve, except we make a square gate and a square body for better and to minimize vibration and to help with cavitation. I can present after this one individual presentations on each of these valves, so we can go into more detail on them. But they're commonly used as outlet valves and guard valves on low-level outlets or sluice drains, valves that are applications where the owner had to like replace a valve or increase the size of the valve. It's important to note that even though we call this a throttling knife gate, it's not really a control valve in the classic sense. So it's not designed to sit there and modulate like a control valve in, say, a process plant. Throttling to us means that we're comfortable with opening it partially open and let it flow indefinitely at that position. It's common that these valves are operated, say, seasonally. So maybe for a few weeks, it's open at a certain position, and then the flow has to increase for a fish migration. They'll open it a little bit and then set it there for a while. So it's not a control valve. It's a throttling valve. We can build these up to about 84-inch. We've actually built them bigger. We just built a 108-inch valve for Houston. But 84 inches, usually on a dam, you won't see much larger than that. An unbalanced head condition, I go back to the head definition that I was talking about. Unbalanced, we're comfortable up to about 200 feet ahead or 85 psi. And if the owner can say, I'll always have the outlet valve closed when this guard valve or isolation valve is open, then we're comfortable with the valve going up being higher, like say 150 psi. Our throttling knife gates have a coefficient of discharge of 0.95. So basically a wide open pipe is 1.0. So there's not a lot of obstructions in the flow path wide open of a throttling knife gate valve. And finally, a VPI, that's just to compare it to the other two valves I'm going to talk about. This is the base, if you will, like a CPI. This is the base price of the three valves. So I'm going to show you a throttling knife gate valve in action at Tiger Creek Afterbay. First, I want you all to go into your chat box and type in there to Kristen and Jack, what animal do you think this is? I've got my guess, but I'm not sure. So this is Tiger Creek Afterbay Dam. It's 2017. There was a huge runoff, so they're opening spill gates and our throttling knife gate valve, which you see right there. It's a 48-inch throttling knife gate, and it sees probably about 40 to 50 feet ahead here. Those are the radial gates I was telling you about. Anyway, this is the second valve that we provide, and that's the Hilton jet flow gate valve, series H2500. It's good for outlet valves at high head dams. You will see customers say, hey, we want it even though the head is lower, but that's because they've got these valves probably installed at other facilities and they like them. But they're really not. To install them on a low head dam is really overkill in my estimation. So a jet flow gate valve is really it's a variation of a knife gate valve that the USBR developed in Denver for to replace failing needle valves. If you're familiar with Hoover Dam, they replace a lot of their large needle gate valves with jet flow gate valves. And like the throttling knife gate valve, it has special features that minimize vibration, cavitation, and galling. And galling is something I can talk about if you have a question about it, bring it up, but I can also talk about that when we talk about these individual valves in a future session. And they're used for outlet valves, like I say, for medium to high head dams. And it has a very energetic discharge. So it's, as the name sounds, jet flow, it's a pretty good discharge. It's really meant to basically just avoid cavitation and get water downstream. We feel comfortable building them as large as 7-foot diameter, and we can go larger on a case-by-case basis. We've got some inquiries now for 90-inch jet flow gates that we've got to think about. Unbalanced head, they can go up to pretty high dams, 250 psi easily, and they're never operated in a balanced condition. They're always an outlet valve. Because they've got a little more in the flow stream, their CD is lower, like 0.84, and they're about 2.5 to 3 times as costly as a throttling knife gate valve, depending on their size and what the head is and materials of construction. This is an example of a jet flow gate valve that we sold to LA County Department of Public Works. It's a 24-inch jet flow in Big Tahunga Dam. You can see that the discharge there is jet-like compared to the throttling knife gate. The last type of valve we build is the fixed cone valve, or the Howell-Bunger valve, and their applications are, again, designed for high head dams, but you'll see owners want to put them on lower to medium head dams too. It's a beautiful, really elegant designed valve. It was designed to operate with minimal power. It's probably its biggest thing, but it also doesn't cavitate, and it just, if you don't have a hood on it, it can be said to dissipate energy 100%, because it just shoots the water out into space until it loses energy and falls to the ground. We feel comfortable building them up to about 7-foot diameter. We're talking actually about maybe finding some outside facilities, or if we get requests for larger valves than that, we might have them built outside. They have a very high unbalanced head. I mean, they can go even higher than 1,000 feet. In Europe, you see them at 2,000-foot dams. They're installed. They have the same coefficient of discharge as the jet flow gate, and they're actually cheaper to build than the jet flow gate because there's less steel in them, and they're a little simpler designed. And most of you have probably operated fixed cone valve. So your standard hose sweeper is a type of fixed cone valve. Basically, this is the same discharge that you would see out of a fixed cone valve. It's a 45-degree kind of radial discharge. Pulling the sleeve back, equivalent of pulling the gate back on a fixed cone valve. And then if you slide the gate forward, it closes it. So that's the same principle that a fixed cone valve operates on. So this is a fixed cone valve actually installed at a dam. That's probably about a 30 to 36-inch diameter fixed cone valve. You can see the discharge is pretty wide. It's pretty wide field. So unless you have a tail race or a downstream area that's pretty wide open, it's going to create a big mist cloud, and that's actually a problem that a lot of operators, once they were installed, said, "Hey, I can't have this cloud. It's freezing up in the wintertime. Everything downstream is causing a problem. So what can you do?" So valve designers designed a hood. So they basically enclose the discharge in a hood to concentrate the flow and keep it from spraying all over the place. This is a 48-inch fixed cone valve hooded. You can see it's still, even with a hood on it, it's a pretty energetic discharge. I mean, your tail race would want to be, rock or concrete or something, because that's just going to erode anything that's in its path. Those are the 3 types of valves, and this slide is to give you a little bit of information on what you should think about when you visit a customer asking about a valve. So what's the size, what type of valve is it, if it's existing, what's vintage, what manufacturer. Those are all things that we need to know. How is it operated is important. Are they going to operate it wide open or partially open? Is the head balanced or unbalanced? It's very important to know. It's good to know how they're going to operate it. What is it, hydraulic, electric? And then if we don't know if they're only giving us the gross head, it's nice to know what the conveyance looks like. So we can kind of estimate, okay, what kind of losses are passing through the dam, so we can derate the head, that net head at the valve. And then finally, it's always good to get photos or drawings of the existing valve or drawings and specs of a new valve. So to wrap up, things I hope that you take away from this session are to understand that the hydrovalve market is driven by, right now, just need to replace older, undersized, or wrong types of valves. That's the most common inquiry we get. Remember that most dams in the U.S. are low medium head, so the throttling knife gate valve is really a valve that it's the value proposition, if you will. I mean, it's the valve that they should really think about. If they're thinking about a fixed cone valve or a jet flow gate valve, and it's a low head dam, it's really not necessary. Now, on a medium head, up to a certain point, a throttling knife gate valve works, but if you get much above 200 feet, you want to start looking at a jet flow gate or a fixed cone valve. And again, on a high head dam, same thing, jet flow gate or a fixed cone valve, and that's driven a lot by what does the tail race look like, or you know, their history with the valves. A lot of times, owners just like jet flow gates, and that's what they're going to get. And then finally, last thing to always remember is that the throttling knife gate valve is not a control valve. So if you get it, if you sense that they're going to operate this valve continuously, open and close or partially open, it's really not the right valve, and that's really not going to be the case at dams. There's very few dam operators that operate a valve in that fashion. And with that, thanks for listening.